Welcome back, folks. Here's another example of writing KCLs for a circuit. It's going to be a bit more of a practical circuit, more similar to what we're going to do in class for sure. It's a circuit that we've seen before. I've just labeled it a little differently. I used this example when we were looking at our KVLs. Okay, so same circuit, but now I have the currents labeled instead of the voltages. Okay, so there's a bunch of nodes that we can pick off here and write some KCLs, and I think it's a little easier to do here because we can hopefully get our pen out. There we go, get our pen out, and let's write one for this node. We can write it for all of the nodes, and we're going to do it. And if you notice, there's one current that I haven't labeled, and we can go find that current using KCL. But let's start with this one, this orange node over here, and we've got to figure out what's going on. So I've got 1, 2, 3 components connected to that, so I'm going to get 3 terms in my KCL equation for that node. This one's going in, okay, so let's start and do this, plus, but it's negative, so I'm going to pull that negative sign in. I'll use the parentheses to kind of make it perfectly clear what I'm doing and why I'm doing it. That comes from the arrow direction. This comes from the label on the current down here. Okay, I've got the same kind of shenanigans going on here where I have this current leaving, okay, and that's going to make it a negative, but the value again is itself negative 1.41. Okay, and that's in amps. All right, last one. This one's going in, so it's plus, and well, it's just plus, but oh, it's in milliamps, and I've been bad. I haven't been writing my units over here. Okay, so we got to be a little careful with units because milliamps is going to have an exponent on it. We're going to make sure we do that when we plug it in the calculator. Now, if we did that correctly, those are the 3 things connected to the orange node over there. And we're going to say that that should be equal to 0. So let's pull out a calculator, turn it back on, and we've got negative 2.05 amps minus a negative, so that's going to be positive, 1.41 amps. And then we have a positive 640 milliamps. So I'm going to get E negative 3 in there, and it wrapped around, but we see E negative 3. And hey, that comes out to 0. Okay, so turns out Kirchhoff knew what he was talking about. And on a good day, occasionally I do too. So that's one example that we can kind of pull out of this circuit for KCLs. All right, let's pick out another node. I don't know, which one do we want to do? I think the only one that we can do that doesn't get us too deep into the problem too quickly is this one here. So let's make that the red node, and I'll solve that over here with red. Again, we have 3 things connected to it, so we're going to have 3 terms. This current is now entering this node. Okay, it was exiting this node. Now as we write the KCL for this one, it's a matter of perspective. You got to remember which node you're writing it for. It's entering, so it's going to be plus, and then the negative gets pulled in with the number. Okay, plus a negative 1.41 amps. This one's going into the red node, so it's going to be plus 2 amps. And then this one's leaving, right? And it's going to be 590 milliamps. If we wrote that correctly, if I pose the problem correctly, that should be equal to 0. And let's plug that all in real quick. Get negative 1.41 plus 2 minus 590 E negative 3. And that ends up being 0. All right. Another point for Kirchhoff. Okay, all the other nodes. How many other nodes are there? How many nodes in the problem? You should be practicing this. Every circuit I put up, you should be trying to identify the nodes. There's 2 more nodes. And the reason I left these 2 for last is because they're both connected to the voltage supply, and we don't know anything about the current through the voltage supply. but we can make a guess on the direction, and then we can solve for it. Okay, so I usually say up or down, and some people pick up, some people pick down, and that's okay. Let's go ahead and pick down. I'm not sure why. Okay, and well, it's red now. That was probably my best arrow of the whole day. Let's make it white. So let's assume this arrow right there. And if I want to write a KCL, I can write it down here. Even if that was ground, I could write it down there. There's still current going in or out of it. The same way all the other nodes have current going in and out of them. So let's make that the blue node. And again, I've got 3 things connected to it. One of them's an unknown now. Okay, we'll just call that I. Okay, so let's see. This current is leaving the blue node, so it's minus, and it's negative 2.05 amps. This current's leaving the blue node, and it's 2 amps. And then this current's entering, so it's plus. And we don't know what it is, so it's just I. Those are all 3 things, so Kirchhoff's current law tells us that it needs to be equal to 0. So we solve for I. Okay, and with I, we find that, let's see, it's going to be, pull both of these over. Let's go slow and do it right? So 2 amps, and then that negative is going to disappear, so it's going to be negative 2.05 amps. And in this case, well, let's go get it out of the calculator. It's far more fun, isn't it? 2 minus 2.05. And once again, engineering notation is going to save us here. We get negative 50 milliamps. Okay. This looks like negative 2 amps and negative 50 milliamps together there. But I don't have to think about it, and that's my favorite thing to do. So it's going to be negative 50 milliamps. So I picked wrong. The current's actually flowing up. But according to this arrow, it's negative 50 milliamps. All right, last node, and I think it's going to be green. Okay, is this node over here. 1, 2, 3 things connected to it. I now know that this is negative 50 milliamps, according to that. All right, let's start up here. This current is leaving the green node. So we get negative 640 milliamps. That's going to be under the calculator. This current's going in, 590 milliamps. This current's leaving, but it's negative, so it's minus 50 milliamps. And that should all equal 0 if we had done this calculation correctly. So we're really checking ourselves. Okay, did I do this this blue KCL correctly? And I can check it by writing the green KCL at the adjacent node. All right, so let's give that a try. Negative 640 milliamps plus 590 milliamps, and then plus 50 milliamps, and we get 0. Okay, so turns out Kirchhoff knows what he's talking about. All right, so I think we have some good examples of KCLs. We're going to write a lot of these, but I wanted to get you some examples up front here so that you got comfortable with the signs and how to handle the signs, and hopefully how to write these consistently, because we're going to use them to perform circuit analysis in the coming chapters. I'm going to revisit one problem. It was the problem that we used when we were talking about passive sign convention and calculating power, whether power was supplied or dissipated. I'm going to go back and revisit that problem. I had filled in a lot of values, and I had filled in a lot of values because I know at the time I knew that I needed to use KVL and KCL to do so. Now you know how to write KVLs and KCLs, so I want to revisit that last example for you and kind of do a bunch of KVLs and a bunch of KCLs to figure out what's going on in that problem, so that if you had seen it without everything filled in, you'd be able to do it regardless. Okay, from there we'll go on and we'll start analyzing circuits. All right, that's going to get exciting. I'm going to teach you how not to analyze circuits, and then I'll teach you the right way to do it. So stay tuned and good luck.